Okay, so tomorrow we are going to take your Unit 7 test. So today we need to review. So this whole thing is just a review of pretty much everything we started since after winter break. So everything we've done this month. So this video might be a little long. So I would encourage you, if you feel like my brain is getting totally just overworked and I need to take a break halfway through, absolutely do that. You can pause this video, go take a walk, go eat a snack, do what you have to do, and then come back. Make sure you come back and finish it. Totally get it. So we're going to do exactly what we did last unit test, the one about natural selection, how we filled out a whole study guide, but just that time it wasn't on like a slideshow like this. I think it just looks a little bit cleaner this way. So it looks like it might be long, but it's no longer than your last study guide was. Promise. Okay, so let's go through and fill in everything we need to know to help you prepare for tomorrow's test. Yippee. Okay, so this very first slide here, remember we started with the layers of the earth. It says, identify the layers of the earth using the picture below. Easy. So here is an earth, and on the right side, it looks like we are looking inside the earth at the actual layers that are present. So this here in the very center of the earth, that is going to be our inner core. Because you can think of, how do I spell? You can think of an apple, how the core of an apple is the very inside. Same thing with the earth, the inner core and then the outer core. Because this core is on the inside and this part of the core is on the outside. Easy. Then number 3, we move up into the mantle. So at first we have that lower mantle, and then on number 4, above that lower mantle is the upper mantle. Don't ask me why for the core we said inner and outer, and then for mantle we said upper and lower. I wish they were the same, but we got to make everything difficult. That's not on me. Okay, and number 5 is that outermost layer of the earth, that top layer. This is the part we're up and walking around on. That is the crust. You can think of a piece of pizza. The outside of that circle is the crust. It's the outermost layer, if you will, of a pizza. So same thing for the earth. The crust is on the outside. Now, you'll remember we broke it down a little bit further. Let me put myself up here. We talked about 2 new layers of the earth that might not be nearly as familiar to us as the core, mantle, crust, all that business. We talked about the lithosphere and the asthenosphere. So over here I've got a picture of both to help you remember. The lithosphere is what we're up and walking around on if it's continental, meaning it's on land, or if it's oceanic lithosphere, it's that top layer of the earth covered by the ocean. Easy. And we remember that the lithosphere is on top of that asthenosphere, which is that hot magma that is mostly in the mantle. So these are some pretty big scientific words. You sound pretty smart when you're throwing these words around. So what we're going to do for each of these statements, these are either facts about the lithosphere, so that top layer, or the asthenosphere that's right below the lithosphere. So let's read through each and put each letter under lithosphere or asthenosphere. Pretty easy. So letter A. It says rocky and brittle part of earth made up of the crust and the uppermost top part of the mantle. So if you look at this picture here, that part of the crust and the part of that upper mantle, that is going to be true for the lithosphere. And like it says, it's rocky. I mean, think about Earth's surface. It's rocky and brittle, meaning it can break pretty easily. So that is the lithosphere. Part B, it is like a conveyor belt for the plates due to convection currents. And we're going to refresh ourselves on convection currents on the next slide because I think that's probably the hardest thing to grasp for this unit. I'm going to be honest. So it acts like a conveyor belt, meaning that it moves and rotates, and things sitting on top of it move as well. So those convection currents in the asthenosphere are what's going to move, and as a result of those convection currents, that lithosphere is what's going to be moving. So the part that's actually working as a conveyor belt, the part that has those convection currents, that is your asthenosphere. Okay. C says Earth's plates are made from this layer. So again, those tectonic plates, the part that we are standing on, or those continents that are placed on, those are going to be in that lithosphere, because again, that is the top layer. D says plastic and flowing layer. I don't think we used the word plastic to describe the asthenosphere when we did our guided notes, but we did say that it is flowing. So it's liquidy, it can move. Think of that magma, it's just kind of floating around, which is going to cause that lithosphere to move. So the lithosphere is super hard and brittle, but that asthenosphere is nice and flowy. It's moving around. And again, you might see plasticky to describe the asthenosphere as well. So that is going to be D. E says this is the layer that the plates float on. And we kind of already answered this. So whatever those plates that are on those lithosphere, they are sitting pretty hard on top of that flowy part that's going to cause them to move. So the layer that the plates are actually floating on top of is that asthenosphere. So that is going to be E. F. It is located in the upper mantle. So this layer has no crust in it. It's all mantle, okay? So if there's no crust present, it's all mantle, meaning it's all magma. That is going to be your asthenosphere as well. It is all flowy magma. G says rigid. Rigid is pretty much saying the same thing as up here where it says rocky and brittle. It's rough. You can think of, I don't know, think of like a super old, dry, stale cookie, how it's rough and brittle and it's hard to break sometimes. That is the same thing as a lithosphere. So G, rigid. There we go. Okay, if some of this stuff that I'm going through, especially this slide, if you're like, oh my gosh, I really have no idea what she's talking about, I don't even remember going over this, go back and look at the guided notes for this part so you can really get a nice refresher. Because again, this is all just basic review. I'm not going into it with super amount of depth because you've already learned all this. So, okay, this slide, we're talking about those convection currents. So again, that magma in that asthenosphere, it's going to move around in a certain way to cause a circular motion to happen. You can think of like a whirlpool. If you've ever got into a swimming pool with you and your friends and you like run around the edge of the pool and it causes like a motion in the water to move. I don't know. I might be aging myself. When I was young, we didn't have like phones to look at. So this is how we entertained ourselves. But if you think of like this constant rotation that causes things to naturally move, that's what a convection current is. So what's actually happening to the magma that's in this asthenosphere to move in that way? So what's going to happen? Step one, you have that cool magma is going to be heated by the Earth's inner core. Okay, so the inside of the Earth, and I'm going to go back up here to show you, the inside of the Earth right here is super hot. The further down into the Earth's center you go, the hotter it gets. So as soon as magma is moving down toward the center, it's going to get hot. It's going to heat up naturally. It's like Earth's little microwave in the center. So after that cool magma is then heated up, that magma is going to become less dense, meaning it is more likely to float or rise up in the liquid, and it's going to rise. So that hot magma is going to rise. Remember how we talked about heat always rises. If you are in an attic of an old house, it's going to be much hotter than the basement because that hot air is going to rise. Same thing with the magma. If it's hot, it's rising. Then when that hot magma gets up toward the tippy top, it's in a much cooler part of the Earth because again, it's cooler up toward the outside of the Earth. So once that hot magma rises, it is going to, well, let's say this. After rising, that hot magma will then cool. So if you even follow these arrows, you've got the hot magma rising. Once it gets up here, it cools off. And once it's cooled off, the now cool, here let me move over. The now cool magma is more dense and will now sink. Okay, so let's go over that again because that can be a lot. You have your magma getting heated up by the center of the earth. Since it's now hot, it is going to rise. And once the magma comes up here and cools down, it's going to become more dense or more likely to sink. And it's going to do just that. It's going to sink. So you constantly have all of this magma moving in that circular motion. And that circular motion is what's called the convection currents, okay? So once you have those convection currents constantly happening in the asthenosphere, those tectonic plates, that lithosphere that's sitting on top, that magma is going to cause those plates to move with it. So that is why those tectonic plates are moving, okay? Because of those convection currents. Great. I know it's kind of crazy to think about, but it's what's happening. Okay, next part. Define continental drift. And as a reminder, this is an idea or a theory that was proposed by this German guy named Alfred Wegener. So what is continental drift? Well, continental drift is exactly as it sounds. It is just a theory or an idea that states that the continents, okay, and remember the continents are like large pieces of land, so we're in North America, South America, Africa, Europe, Asia, those are the continents. So it's a theory that states that the continents were once connected together, so they used to all be one massive continent instead of separate continents that we have today, in a giant land mass, like I said, just one piece of land called Pangaea. Okay, so that's step one. So here, right there, how it's all one piece of land, that was one supercontinent, that was called Pangaea. So they eventually broke apart and drifted or moved to their current location. And obviously, I just typed a lot kind of quickly, so if you need to pause the video, pause it, get it all down before you move on. So a long time ago, millions of years ago, all the continents were together as one massive landmass. And then because of those convection currents, because of those constant circling of the magma in the asthenosphere, that lithosphere moved. So the continents on those tectonic plates slowly drifted apart until they are where they're sitting right now as separate continents. So that is what the deal is with continental drift. Now here's the part that we kind of struggled more with during our independent practice, or what I noticed we seem to struggle with. So continental drift at first was kind of like a crazy theory. Like if somebody just walked up to you on the street and were like, the continents move, you'd be like, no way, this man's nuts. But it's true. And we have evidence that supports this idea. So it's not just like a crazy idea. We have multiple pieces of evidence that prove that continental drift is a real thing, okay? So these are the 4 pieces of evidence that we have to support this theory that the continents move, okay? So what are these 4 pieces of evidence? Well, first, we have the continents fit together like puzzle pieces. Honestly, that's enough right there to convince me that it's true, but whatever. So if you look at the map, all of today's continents, they beautifully, if you just squeeze them together, they fit together perfectly like a little puzzle. So that shows that at one time, they must have been connected, okay? I think that's the easiest one to understand. Then we get a little bit more freaky, okay? So over here we have what we call our fossil clues. So with fossil clues, you have similar fossils that can't swim. This is key. They can't swim. They are found oceans away from each other. Okay, let me break this one down a little bit more because this is where it gets confusing. At one point, South America and Africa right here, these are our examples, they were joined together. So they're one massive piece of land. We have found fossils in both of these continents. Fossils for the same exact species and they're the same exact age. Okay, so they must have been related. They're the same species. However, let's look at this fossil right here. This fossil, the animal that this fossil belonged to, can't swim across an ocean. That's way too far. It would get tired and drown. Tragic. So we know, okay, this fossil is for an animal that can't swim, so it must have been able to walk between continents. So clearly, this used to be one piece of land, so this piece of land was actually joined with this piece of land. So realistically, this wasn't a massive amount of land because they were connected. So the fossils didn't just like magically appear across the ocean. They were once together. That's what fossil clues is all about. Okay. Now we also have those climate clues. So we have evidence of glaciers or large hunks of ice that are in continents that are now too hot for ice. Okay, so what do I mean? What am I talking about? So these right here are those glacial striations or cuts in rocks that were made from big pieces of ice, okay? Now, so what? Who cares about that? If you think about continents today that are super hot, like think about Africa. If you don't know this already, Africa is like way too hot and way too hot to support massive amounts of ice, right? So we know at one point Africa must have been located somewhere much cooler. So if you think about Antarctica, Antarctica is down more towards the bottom. Antarctica is very cold. There's nothing but ice there, like literally nothing but ice. So we know Africa at one point wasn't where it is in the earth now, where it's super hot. It must have been located further south, where it's nice and cool. So that's what that whole glacier evidence is about. And last one, we have that rock evidence. So we have that mountains made of very similar rocks line up when the continents are together. Okay, so we have a mountain range in North America called the Appalachian Mountains. They're actually very close to us. They run through Tennessee and many other states, but Tennessee's right there. And there's another mountain range called the Caledonian Mountains that are in Europe, which is all the way across the ocean from us. The rocks in both of these mountain ranges not only are the same type of rock, are the same age, but also when you line up the continents, put them together like those puzzle pieces that they are, that mountain range lines up beautifully, like it's one long string of mountains, okay? So that is another piece of evidence. So there's evidence all around us. So continental drift, it's real, y'all. It's real.